Have you ever been at a packed stadium or maybe just a super busy downtown street staring at your phone? You've got full bars, right? But literally nothing is loading. It's so frustrating. Well, that right there is the classic symptom of network congestion. Behind the scenes, your local cell tower is basically maxed out, desperately trying to juggle way too many users all at once. But what if that tower could automatically, seamlessly slide your connection over to a parallel, less crowded frequency, and do it without you even noticing? That's exactly what we're getting into today. Welcome to The Explainer. Today we're zooming in on a highly technical, behind-the-scenes hero of modern cellular networks. It's called LTE 170, or, if you want the full engineering name, Inter-EMB Interfrequency Load Balancing. We're going to demystify this whole engineering concept today, and here is our roadmap. We've got 6 main areas to cover. First, an introduction to LTE 1170. Second, the 4 building blocks making it work. Third, how we actually measure cell load. Fourth, finding the right UEs to move. Fifth, executing the handover itself. And finally, the configuration and deployment rules. All right, let's jump right in. Section 1, Introduction to LTE 1170 and how it solves network congestion. So think of a cellular network like a massive, multi-lane highway. Without a feature like LTE 1170, it's kind of like everyone trying to cram into the left lane. Let's call that frequency 1. Obviously, the utilization gets completely imbalanced. That lane gets so unbelievably crowded that some cars, or in our case, UEs, which is just engineering speak for your smartphone, well, they just aren't getting scheduled to transmit data. They're basically stuck in traffic. But turn LTE 1170 on, and suddenly it's like a really smart traffic controller steps in and opens up toll gates to parallel totally open lanes on different frequencies. The result? Resources are vastly better utilized, and way more users actually get to send and receive their data. So what exactly is it? Well, the crucial thing here is the definition itself. LTE 1170 is a network feature that builds on top of previous capabilities. Specifically, it extends the intra-ENOB load balancing of an older feature called RL40. Its whole job, its entire purpose, is to move incoming load from a highly loaded serving cell over to low-loaded neighbor cells that are operating on an entirely different frequency. Now, a quick caveat here. The goal actually isn't to make every single cell exactly equal. Nope. It's really just to keep the load of every cell safely below a specific, manually configurable threshold. Moving on to Section 2, the 4 building blocks, or how this thing actually functions under the hood. Okay, so LTE 1770 relies on 4 very specific sequential pillars to get the job done. Step 1 is load supervision and exchange. Basically, the towers actually have to realize they're congested first, right? Step 2 is candidate UE selection. The system has to pick the exact right users to move. Step 3 is measurement solicitation, which is essentially the network asking the chosen phone, hey, can you actually see the alternative tower from where you're standing? And finally, step 4 is the IFLB execution, the actual seamless handoff. Which brings us to Section 3, measuring cell load, the first pillar. Every 500 milliseconds, literally twice a second, the eNode B, your cell tower, calculates 3 highly specific types of load. First up is the downlink guaranteed bitrate, or GBR load. This one tracks the heavy lifting, for things that absolutely need a steady connection, like a live video feed. Second, we have the downlink non-GBR load. This estimates the capacity for things like background downloads. And third is the PDCCH load, which essentially monitors the control channel's bandwidth, kind of like the administrative overhead. If any one of these 3 metrics crosses its high load threshold, boom, the cell immediately enters an active load balancing state. Now check out that large 0.5 filter coefficient, known as alpha. This is super important because network traffic is incredibly spiky. Imagine 100 people clicking a viral video link at the exact same millisecond. You'd get a massive, instantaneous spike. If the tower reacted to every single raw spike like that, users would just be ping-ponging between towers constantly, and it would be a huge mess. So by using a 0.5 filter, the system takes 50% of the past filtered load and 50% of the current load. It beautifully smooths out the curve and prevents the whole algorithm from overreacting. But here's the thing, measuring your own load just isn't enough. You really need to know how busy your neighbors are too. So while a cell evaluates its own load every 500 milliseconds, it actually exchanges its available capacity with other cells belonging to the exact same eNode B every 1 second. And this exchange happens constantly, whether load balancing is triggered or not. It keeps the whole system perfectly primed with fresh data, so it's always ready to act. All right, Section 4, finding the right UEs, who gets offloaded? This timeline is absolutely crucial for understanding the actual user experience. The system specifically targets phones that are just waking up, devices moving from an idle state into a connected state. Why? Because it really doesn't want to interrupt someone who's already deep in a data session. So when your phone connects, a timer starts. When that timer expires, the network checks a few things. The most important question it asks is, did you just establish a QCI1 bearer? Now, that's just engineering speak for a voice call. If you did make a call, you get an exemption. The network is definitely not going to risk dropping your active phone call just to save a little bandwidth. But if you're just, say, browsing the web, the network goes ahead and activates what's called an A4 measurement. It's basically tapping your phone on the shoulder and asking, hey, can you hear that other frequency clearly?
And that takes us to Section 5, executing the handover, making the jump.
The network doesn't just blindly throw you over to any available tower, though. Not at all. It applies a really strict set of elimination rules to its target cell list. For instance, if the signal strength or quality, the RSRP and RSRQ parameters are too weak, that target is immediately eliminated. Cross it off. If the target cell is actually full itself, it's out. What if the target cell recently rejected a handover and is sitting on a temporary blacklist? Yep, you guessed it, it's out. And if the target happens to be a completely different technology type or maybe a private home eNode B, it's eliminated too. We only want to move the user if the destination is actually going to be a better experience. For the lucky few cells that actually survive that brutal elimination process, the eNode B ranks them strictly by descending composite available capacity, or CAC. Simply put, the cell with the most available, free room, goes straight to the very top of the list. And that number one spot? That is the specific target chosen for your phone's seamless handover.
Let's look at Section 6 now, configuration and deployment rules, the control dials.
Okay, let's talk about the concept of hysteresis, which is a fundamental rule in network engineering. Take a look at the gap between the target load and the high load. Say an engineer sets the high load to 60% and the target load to 50%. The cell won't start kicking people off until it hits that 60% congestion mark. But, and here's the clever part, once it does, it won't stop load balancing until the traffic drops all the way back down below 50%. Leaving that gap is absolutely critical because it prevents the network from constantly turning the feature on and off, if the traffic is just hovering right around, say, 59%. Engineers can actually do some really clever things with these parameters. For example, if they set a cell's target load to 0% and the high load to 100%, they effectively completely exclude that cell from load balancing altogether. Or, if they set the target to a normal value but leave the high load maxed out at 100%, that cell basically becomes a sponge. It will happily accept offloaded users from all its neighbors, but it will literally never offload its own users. It just gives network operators this incredible, granular control over how traffic flows through their systems.
But, of course, there is a catch. What do you think happens if a feature called LTE 55 is turned off? Well, the answer is pretty simple. LTE 1770 completely fails. LTE 55 is the core capability that actually allows a phone to jump between frequencies in the first place. So without it enabled at the deployment level, all of this brilliant load balancing logic we just talked about is totally useless. It is an absolutely mandatory prerequisite.
So, as we wrap things up today, I want to leave you with a bit of a provocative thought. We've seen just how delicate the balance of these manual parameters really is, right? Well, as network loads continue to grow exponentially with 5G and whatever comes beyond that, how will these highly sensitive tuning dials, like estimating those non-GBR weights, need to evolve? Are we going to see machine learning step in and take over these manual thresholds to perfectly optimize traffic in real time? It is a fascinating space to watch, and understanding these exact foundational mechanisms is really the key to unlocking the future of automated networks. Thank you so much for joining me on this deep dive through the explainer, and keep learning.